It's a little after 5 in the morning, and most of Washington is still asleep. Then, without warning, the darkness breaks. A single flash floods the sky, brighter than the full moon, throwing pale light across mountains and rivers and rooftops for a fraction of a second before the night closes back in. For a moment, nothing follows. No sound, no explanation. Then a low, rolling thunder arrives late, moving across the state in a way no storm ever does. Phone lines flood, and 911 dispatchers take call after call from people who saw the same impossible light and can't agree on what it was. Miles away, in quiet rooms full of humming machines, sensors twitch. Instruments built to listen to the whole planet register a pulse of energy, and their numbers line up on a single conclusion. The instruments agreed a 10-ton blast had gone off over the state, and yet, to understand how a piece of the sky could arrive completely unannounced, you have to rewind to the last ordinary minute before it did. A quiet sky, so rewind. It's the small hours, and Washington is doing what it does before sunrise. The highways that carry hundreds of thousands of cars a day sit nearly empty, just a scatter of headlights sliding between the towns. Streetlights hum over quiet intersections. Somewhere a truck downshifts on a long grade, and then even that fades. Overhead, the sky is clear and cold, the kind of deep, still air that comes with a high-pressure night in early spring. The stars hold steady. There's no moon glare, no cloud, nothing to draw the eye upward, and almost no one is looking up anyway. That's the strange truth about the sky above us. We treat it like a ceiling, a fixed thing we stopped watching long ago. Radar tracks the planes, and the rest just drifts past unnoticed. For a few more seconds, everything was ordinary, but a single point of light was about to grow brighter than anything anyone in the state had ever seen. The flash. It begins as almost nothing. A faint point high in the dark, the sort of thing you'd mistake for a satellite or a slow-shooting star if you happen to catch it at all. Then it grows. Within a heartbeat, that point swells, gaining speed and brightness, pulling color out of the black. It turns from white to a fierce blue-white, and the intensity keeps climbing. For a stretch of seconds, it hangs there like a second sun switched on in the wrong half of the day, flooding the landscape with hard, sudden light. Shadows snap into place across frosted fields. The struts of a bridge, a line of fence posts, the shape of a car on the freeway, all of them throw crisp, black shadows that swing as the light moves overhead. Drivers flinch. The light arrived in perfect silence, and that silence was the strangest part, because the sound had not yet begun its long journey down. The sound. Then, seconds after the light, the air itself changes. A low front of pressure rolls across the land, and it does not sound like thunder so much as feel like it, a deep push against the walls and the ground and the soft space behind your ribs. The sound lagged because light and sound do not travel together. The flash crossed the sky in an instant, but the boom had to grind its way down through miles of cold air at barely 1,100 feet per second, and every mile added roughly 5 more seconds of waiting. So the sky flared, and the world went quiet. And then long after the glow had faded, the noise finally arrived to collect its debt. People felt it in their chests before they understood it, and their first instinct was not wonder, but fear of something far more human-made. The first calls. Within a minute, the phone lines light up. Someone is sure a gas main went. Someone else swears a jet came down behind the tree line, and a third caller, voice shaking, uses the word bomb before the dispatcher can finish the greeting. The calls come in from towns 40 and 50 miles apart, and that is the part that makes no sense to anyone listening. A single explosion should have a single neighborhood, one street with broken glass and smoke, not a whole region reporting the same shudder at nearly the same moment. Emergency lines fill with people describing the same event from wildly different places, each certain the source was just outside their own window. Dispatchers searched for a downed plane or a factory blast, but every place they looked was perfectly intact. Windows rattle. The pressure wave keeps moving, spreading out in a widening ring the way ripples leave a stone dropped in still water. It reaches windows and finds them, like a hand pressing flat against the glass, and across whole subdivisions' panes, rattle in their frames all at once. Car alarms wake in parking lots miles apart, a scattered chorus of horns and chirps triggered not by any touch, but by the ground itself flexing beneath the tires. Dogs bark down entire streets. Picture frames tilt on their nails. You could almost trace the wave by the noise it left behind, town after town lighting up in sequence as the front swept through. The shaking crossed county lines in a pattern no earthquake would ever make, which meant the source was not in the ground at all. Doorbell cameras. In driveways and on porches all across the state, tiny lenses were already watching. Doorbell cameras meant to catch package thieves, dash cams left running on parked cars, security systems pointed at empty backyards. None of them were aimed at the sky, and yet all of them caught it. The footage shows up the way these things always do, one clip at a time. A porch light flickers, then the whole frame goes white for an instant. The shadows swinging hard across a lawn, like a second sun had risen and set in the space of a breath. Somewhere, a dog starts barking before the sound even arrives. Dozens of these recordings existed before anyone thought to look for them, scattered across cloud servers and phone galleries in towns that never compared notes. Each grainy clip captured only a sliver of the sky, yet stitched together they hid a secret nobody had thought to ask for. 9 seconds. Play any single clip, and the whole thing is over almost before you register it. The brightening, the flare, the fade back to ordinary night, all of it fits inside about 9 seconds. Slower than a lightning strike, faster than a shooting star you'd point at and call to a friend. 9 seconds is nothing. It's less time than it takes to read this sentence aloud, less than a held breath, less than the pause between knocking on a door and hearing footsteps. And into that narrow window, the sky poured something it had been carrying toward us for longer than there have been eyes to see it. The people who saw it live barely had time to turn their heads. By the time they thought to grab a phone, the light was already gone, and only the sound was left rolling in behind it. 9 seconds was all the warning the planet got, and no telescope on Earth had used a single one of them. The reports flood in. By the time the sun came up, the phones and inboxes were already full. Fireball reporting networks, the quiet volunteer databases where people log strange lights in the sky, began filling with entries stamped from the same night, the same minute, the same handful of seconds. The reports came in from more than one state, hundreds of them, then well over 1,000 as the morning wore on. Farmers, night shift drivers, a couple standing in a parking lot, someone letting the dog out one last time, strangers who would never meet, all describing the exact same tear across the darkness. Read enough of them and a shape starts to form out of the noise, a consensus built from people who had no way to coordinate. They agreed on the color, they agreed on the low rumble that followed. The reports agreed on the light and the sound, but they wildly disagreed on one thing that would matter more than any other. Not a plane. The first thing investigators do with a blast like this is call the airports. Every aircraft over the region that night had a flight plan, a transponder, a trail of data following it across the map. And when they counted, every plane that took off had landed. Nothing was missing. There was no wreckage on any runway, no scorched hillside, no debris scattered across a field for search teams to comb through. A jet breaking apart at altitude leaves a signature you can't hide. It rains metal for miles. Here, the ground held nothing but startled people looking up. No sonic boom matched a known supersonic flight. No military exercise had been scheduled. The one explanation that would have let everyone sleep easy simply wasn't there. With the sky's own machines accounted for, attention turned upward, past the height any plane could ever reach. Not lightning, so they turned to the weather, because a bright flash and a rumble sounds a lot like a storm. Meteorologists pulled the radar loops for that stretch of Washington. The sky had been clear and cold. No cells, no fronts, no towering clouds anywhere near the flash. Lightning detection networks track strikes across the country to within a few hundred meters, logging tens of millions of them a year. On that night, over that patch of sky, they recorded nothing, not a single spark. The one force in nature that flashes and booms in the same breath had an airtight alibi. No power lines had failed, no transformers had blown. There was simply nothing electrical to blame, and that absence was louder than any answer. Every ordinary cause had been crossed off the list, which left only the extraordinary, and the extraordinary leaves records most people never see. The silent sensors. While thousands of people were fumbling for their phones, other things had already noticed. Not eyes, not cameras, machines, instruments scattered across the planet that never sleep, never blink, and never care whether anyone is watching them work. Some were built to catch the faint tremor of an earthquake. Some listened for sounds too low for any human ear. Some stared at the sky night after night for reasons that had nothing to do with a flash over Washington. None of them were designed to solve this. All of them had a piece of it anyway. That's the strange comfort of a modern sky. It's crowded with quiet witnesses, and they keep their own diaries in numbers. Somewhere in a government archive, a set of instruments designed to watch for weapons had just logged something falling out of deep space. Eyes that never blink. High above the weather, in orbits that circle the planet, sit satellites that never sleep. They were built for one grim job: to spot the heat of a missile the moment its engine lights. Their infrared eyes are tuned to catch a sudden bloom of warmth against the cold curve of the Earth. But those same sensors don't care what makes the heat. A rocket plume and a rock burning through the upper air both glow in the same wavelengths, so the satellites catch fireballs by accident, dozens of them every year. When something falls out of deep space and lights up, these watchers see it long before any human looks up. So when the flash tore across the sky over Washington, it registered far overhead as a spike of infrared, logged and time-stamped by hardware most people will never know exists. These silent watchers had timed the flash to the fraction of a second, and their data would soon put a hard number on the blast. The infrasound web. There's another network listening, and it works far below the range of your ears. Scattered across the globe are stations that catch infrasound, sound so low and slow that a person standing right beside one would hear nothing at all. They were strung together to enforce a treaty, to catch anyone testing a nuclear weapon in secret. A big explosion doesn't just make noise you can hear. It pushes out long, deep pressure waves that roll through the atmosphere for hours, bending around mountains and sliding over oceans. These stations wait patiently, and when those slow ripples finally arrive, they trace them back to a source and read the size of whatever made them. An airburst high in the sky is exactly the kind of thing they're tuned for. The rumble spread outward for thousands of miles, sinking beneath human hearing, and the sensors caught every slow beat of it. The same array that listens for hidden bombs had heard this one clearly, and it could measure a blast from thousands of miles away. A voice in the ground, and then there's the ground itself. Buried in bedrock all over the world are seismometers, delicate instruments meant to feel earthquakes stirring deep inside the planet. They spend their days recording the faint tremors of a restless world, needles tracing lines that almost never mean the sky. But a shock wave born in the air doesn't stay in the air. When the blast wave came racing down and slammed into the earth, the ground flexed, just slightly, and the seismometers felt it. On their charts, a sharp little pulse appeared, arriving at the exact moment the pressure hit, a tremor with no fault line behind it. So now a third witness had spoken, one that studies stone and never once glances upward. 3 separate systems, none of them built to watch the sky, had all recorded the same instant, and together they were about to weigh the explosion. 10 tons. When the numbers finally lined up, the answer was quieter than you'd expect, and somehow that made it worse. Take the pressure wave the barometers caught, fold in the timing the ground itself had whispered, match it against the arc the cameras traced, and the 3 witnesses agree on a single figure. The blast released energy equal to roughly 10 tons of TNT, detonating not on the ground, but high in the air above you. There was no crater, no fireball crawling across a hillside, no rubble to sift through. The whole thing happened in the sky, a pocket of the atmosphere suddenly torn open and slammed shut, the force radiating outward in every direction at once. That's why the windows rattled from horizon to horizon, instead of a single street feeling it. 10 tons of force sounds like a monster, yet the thing that unleashed it was almost embarrassingly small, and where such a small traveler had come from was the real puzzle. How big? To find the size, scientists worked the problem backward. Energy comes from mass and speed, and the speed of something falling in from space is brutal, tens of kilometers per second, fast enough to cross a city in the time it takes to blink. Plug in that velocity, and the leftover mass turns out to be only a few tons of solid material. So picture the object itself, not a mountain, not even a house, a single boulder, maybe a meter or two across, tumbling silently through the dark for who knows how long before it met the top of your atmosphere, something you could have stood beside and looked over the top of. That's the part that settles uneasily in the mind. It was barely the size of a car, which raised an unsettling question no one wanted to answer. Why had nothing on Earth seen it coming? The missing warning, because on the night it arrived, not one telescope was watching it. Not a single survey had logged it. No observatory had flagged it days earlier. No automated alert had ever pinged with its name. The rock crossed the entire solar system and closed the last stretch toward the planet in total anonymity. And it isn't as if no one was looking. All over the world there are dedicated instruments that scan the sky night after night, cataloging moving points of light, plotting orbits, quietly building a list of everything that might one day come close. Their whole purpose is to notice objects exactly like this one before they hit. Yet this boulder slipped past every last one of them and only announced itself in the instant it burned. The world's asteroid hunters had missed it completely, and the explanation for that blindness would turn out to be almost poetic. Why telescopes failed? The great sky surveys work by patience. Wide cameras sweep the same fields night after night, and software compares each frame to the last, hunting for a single point of light that moved when everything else stayed still. A big asteroid, kilometers wide, reflects enough sunlight to be caught weeks or months out. But this rock was only a few meters across. At that size, it stays fainter than the faintest stars a survey can register, sometimes until the final hours before impact, and often not even then. There simply isn't enough reflected light to trip the alarm while it's still far away. So being small was one reason it went unseen. Yet small was only half the reason it stayed hidden. The other half was the exact direction it came from, and that direction points straight at the answer we're chasing. Out of the sun, picture the sky split into two halves. There's the night side, dark and quiet, where a telescope can pick out a moving speck against the black, and there's the day side, washed out by the one light no camera can ignore. An object drifting in toward Earth from the daytime side of the sky sits in front of the sun's glare. It's there, moving, closing the distance, and completely drowned in brightness. No ground telescope can separate a dim, meters-wide rock from the flood of light behind it. That's the strange twist. The very brilliance that lets us see everything else is the thing that blinds us to what's coming. It had ridden the glare of the sun all the way in, like a hunter using the light to hide, but hunters come from somewhere. The sunward blind spot. This isn't a flaw in one instrument or a bad night at one observatory. It's a permanent gap in how we watch the sky. Roughly half of the space around Earth, an entire sunward hemisphere, is closed to ground-based eyes because the sun is sitting in it. Anything approaching from that direction stays invisible until it either swings around into the dark or arrives. We've mapped millions of asteroids in the night side of the sky and built a blind spot the size of half the heavens on the other. So when something does come out of the glare, we're left reading the story backwards, from the wreckage instead of the warning. If danger can hide in the daylight, then the only way to know an object's true home is to reconstruct where it had been, and the clues were already scattered across the state. Triangulating fire. A porch camera in one town caught the flash reflected off a car hood. 20 miles away, another saw it low against the tree line. Neither knew what the other had recorded, and on its own, each clip was almost useless. But investigators knew where every camera stood, down to a few feet, and they knew exactly when each frame was taken. Combine a known position, a known time, and the angle to the light, and you get a line pointing out into the sky. One line tells you almost nothing. Two lines crossing tell you a single point in the air. So they gathered them all. Satellite fixes from above, doorbell clips from below, and the shaky memory of drivers who described where the fire hung over the road. Each observer, willing or not, had marked one sightline into the dark. Each camera had seen only a fragment, but geometry does not forget, and slowly, a single glowing line was being drawn across the sky. The steep angle. When the lines were stacked together, they didn't lie flat across the horizon. They plunged. The object had come down at a steep angle, closer to falling than skimming, driving toward the ground instead of grazing the top of the air. And it was fast, tens of kilometers every second, faster than any rifle round, fast enough that the atmosphere in front of it couldn't slide out of the way. That trapped air compressed, heated, and glowed white, and that glow is the flash the cameras caught. A steep, fast entry means the rock pushes deep before the pressure tears it apart. It doesn't fade out gently, high and quiet. It punches down into thicker air, holds together a little longer, and then lets go all at once, low enough for the ground to feel it. The line pointed down toward the ground on one end, but it was the other end, the end pointing back into space, that would eventually tell the whole story. A line in the dark, with the angle measured and the speed pinned down, the path stopped being a guess and became a number, a single vector through the atmosphere, with a heading you could write down and a velocity you could trust. They knew where it had entered, how steeply it fell, which direction it was traveling, and how quickly. Everything scattered across a dozen frightened witnesses and silent machines folded into one clean arrow through the sky. And that arrow didn't stop at the edge of the air. Extended upward, out past the clouds and the satellites, it kept going, a straight thread reaching back toward wherever the rock had begun its fall. For the first time, they had a direction, and a direction, followed far enough, becomes an address in the solar system. Chasing fragments. A direction is a beautiful thing, but it only points. It can't tell you whether anything reached the ground to be found. So the question quietly shifted. Not where did the light come from, but did any of it survive? When a rock this size hits the air, most of it is spent as light and sound and heat, torn apart miles above the surface. The blast you'd already traced was the sound of it losing that fight. Whatever was left would be smaller, cooler, and falling silently now, no longer glowing, just dropping through the dark toward the trees below. That's what turned a wave of physicists into a search party, not for the fireball, which was long gone, but for the leftovers, cold, dark crumbs of something that had traveled a very long way to get here. If even a single stone had survived the fall, it would carry a message written billions of years before humans existed. The fall zone. Finding those crumbs meant answering a smaller, harder question. Once the fireball stopped glowing, where exactly did the pieces go? A meteor doesn't drop straight down. It slows, and the wind takes over, and lighter fragments drift farther than heavy ones. So the searchers fed everything they had into the models. The angle of the trajectory, the height of the blast, the speed at the moment the light went out, and the winds blowing across every layer of air that day. Out of all that came a shape on the map. Not a dot, but a long, narrow strip, tapering the way a scatter of stones spreads across the ground. That strip is called the fall zone, and it's where hope and doubt sit side by side. The math can point you at a few square miles. It can't promise there's anything there. Somewhere in a few square miles of forest and field, pieces of another world might be lying in the dirt, waiting. Black stones, If you've never seen a fresh meteorite, you might walk right past one, but to a trained eye, they stand out. As the rock tore through the air, its outer skin melted and flowed backward, then froze into a thin, dark shell called a fusion crust. That crust is often matte black, sometimes glossy, like the stone was dipped in something and left to dry. That's the giveaway. Against pale soil, snow, or a plowed field, a black stone with smooth, flowing edges just looks wrong, too dark and too clean to belong. Searchers walk slow lines across the fall zone, eyes down, learning to notice that one shade that doesn't match the ground. And when a hand finally closes around one, the first surprise is how ordinary it feels. Cool, dense, a little heavier than it should be for its size. A stone like this weighs almost nothing in the hand, yet it carries a history heavier than anything on Earth. What rock remembers? A meteorite isn't just a rock, it's a recording. Every mineral inside it froze into place under particular conditions, and those conditions leave marks that don't fade with time. Cut one open, polish the face, and you can begin to read where it has been. Under a microscope, thin slices reveal tiny beads of once molten material, crystals that grew slowly in one spot and quickly in another. The size of a crystal tells you how fast it cooled. The chemistry around it tells you what was nearby while it formed. Nothing here is decoration. It's all data, held perfectly still. Scientists treat a fragment like this the way an archaeologist treats a sealed tomb. Every grain sits exactly where physics left it, undisturbed by wind, water, or living things. Locked inside the stone was a record of temperature, pressure, and time, and reading it would reveal a birthplace far from here. Older than Earth. To read that record, you reach for the clock hidden inside the atoms themselves. Certain elements decay at rates that never waver, ticking down over spans no human lifetime could ever feel. Measure how much has already changed, and the stone quietly tells you its own age. When the numbers came back, they didn't point to thousands of years, or even millions. They pointed to the very beginning, to the moment dust first gathered around a young sun. This material is older than the oceans, older than the continents, older than the ground beneath your feet. The Earth formed from the same era of debris, yet this fragment never joined a planet. It stayed small, stayed cold, and stayed unchanged while whole worlds assembled around it. It had existed for 4.5 billion years, waiting, and its final journey had begun only recently, with a violent event we could still find. The first, fingerprint, age, tells you when. The next question is what, and for that you study proportions. The ratio of certain oxygen isotopes works like a signature, subtly different for every kind of parent body in the solar system. Each family of worlds formed at a different distance from the Sun, out of slightly different material, and that difference is baked into the rock forever. Comets carry ice and loose, fluffy dust. The Moon carries the chemistry of a scorched, airless crust. Mars leaves faint gases trapped in glass that match its thin red sky. This stone matched none of them. Its minerals ran dry, its metals were plentiful, and its isotopes clustered in a narrow range all their own. The chemistry ruled out comets and ruled out the Moon and Mars, which left one vast, crowded neighborhood as the suspect. A stranger's chemistry. Strip away the comets, the Moon and Mars, and what's left in the fragment's chemistry tells a quieter story. There's no thick vein of iron running through it, no icy skin that once boiled off near the sun. It's rock, plain and dense, the kind of stone you could hold in your hand and mistake for something dug out of a quarry. That places it among the ordinary chondrites, the most common meteorites to ever reach the ground. Common, yes, but common the way a single grain of a specific beach is common. They're minerals formed in the warm inner reaches of the young solar system, close enough to the sun that ice never had a chance to settle in. So we know its rough address now, a stony body, not metal, not frozen, cooked and pressed in the crowded lanes between Mars and Jupiter. And that narrowing carries a strange weight with it. This kind of stone almost never travels alone. It breaks away from something much larger, and that larger something leaves a family behind. The broken parent. Picture the belt not as a peaceful ring, but as a slow demolition yard. For 4.5 billion years, asteroids have been drifting into one another, sometimes grazing, sometimes striking hard enough to shatter. Every collision sprays out shrapnel, and most of the small stones that fall to Earth are exactly that, splinters knocked loose from something far older and far bigger. Our visitor, at 10 tons, was barely a chip. Its parent might have measured tens of kilometers across, a mountain adrift in the dark, whole and quiet until the day it wasn't. Somewhere in deep time, that mountain met another, and in an instant it came apart. The fragment that lit up the sky over Washington was one grandchild of that ancient blow, carried on an orbit set in motion long before oceans filled on Earth. To find where our visitor was born, we would first have to find its shattered parent, and asteroids leave scattered siblings across the sky. A family of stones. When a large asteroid breaks apart, its pieces don't scatter at random. They drift outward together, keeping nearly the same tilt, the same distance from the sun, the same slow rhythm around it. Astronomers call these clusters asteroid families, and each one is the wreckage of a single collision, frozen into the shape of thousands of shared orbits. There are dozens of them out there, the Vesta family, the Eos, the Coronis, the Themis, each a swarm of stones that once fit together as one body. And because they came from the same parent, they carry the same chemistry, the same fingerprint written into every fragment, no matter how small. That's the thread we can pull. A stone's minerals and isotopes don't just tell us what it is, they tell us who its relatives are. If we could match the fragment to a family, we could rewind its clock by millions of years. But first, we had to go to where the families live. The belt. Picture the space between Mars and Jupiter, a ring so wide that light from the sun takes tens of minutes to cross it. This is the main belt, and if you imagine it as a crowded field of tumbling rocks, you've imagined it wrong. Spread across that gap are millions of asteroids, yet the emptiness between them is so vast you could drift for years and never see one. The pieces come in every size. A few, like Ceres, are round worlds hundreds of kilometers across. Most are dark, irregular boulders, chips and gravel left over from a time before the planets finished forming. Nothing tidy holds them together. They simply circle the sun, cold and slow, in orbits that take 3 to 6 years to complete. Add every asteroid in the belt together, and you still wouldn't have the mass of our moon. It is less a barrier than a whisper of debris, scattered thin across an ocean of dark. Somewhere in that immense sparse ring, a specific patch of orbits was quietly leaking rocks toward Earth, and one of them had our name on it. The gaps. Look closely at how those orbits are arranged, and something odd appears. At certain distances from the sun, the belt thins to almost nothing, as if a hand had reached in and swept whole lanes clean. These empty bands are the Kirkwood gaps, and they aren't random. Each one lines up with a rhythm set by Jupiter. It works like a swing pushed at just the right moment. A rock orbiting at one of these distances circles the sun in a neat fraction of Jupiter's own year, maybe twice for every one of the giant's laps, or 3 times for every one. That timing means Jupiter tugs the rock from the same direction over and over, and those tiny pulls stack up. Given enough orbits, the nudges stretch the rock's path into a long, lopsided ellipse, one that eventually crosses the track of Mars or Earth. That's why the gaps stay empty. Anything that wanders in gets flung out. These gaps are the doors out of the belt, but a rock cannot open one on its own. Something has to push it, patiently, over ages. Sunlight's push. That something is sunlight, and the way it moves a rock is stranger than it sounds. A small asteroid slowly spins, so its afternoon side, warmed all day, carries heat around before it lets it go. When that warm surface finally radiates its heat back into space, the escaping warmth gives the rock the faintest kick, like heat leaving your skin at dusk. One kick does nothing, but the asteroid turns again and again, radiating a little push with every rotation, always in roughly the same direction. Astronomers call this the Yarkovsky effect, and the force is almost absurdly gentle, weaker than the weight of a feather resting in your palm. Yet time is patient, and the belt has billions of years to spare. Over millions of orbits, those feather-light nudges add up, moving the rock a fraction of a kilometer a year, then thousands of kilometers, then farther still. A push no stronger than a whisper had steered a boulder across the solar system, drifting it inch by inch toward one of those open doors. The slow escape. Eventually the fragment drifts to the edge of one of those gaps, a stretch of orbit where Jupiter's rhythm and its own line up in a quiet, dangerous harmony. Each time the two swing past each other, the giant tugs at the same spot, in the same direction, and the pull no longer averages out to nothing, it stacks. The orbit begins to stretch, an ellipse pulled longer and thinner with every pass. For a while, the change is invisible, hidden inside numbers no eye could ever see. Then the far edge of the orbit climbs, the near edge dips, and the rock starts crossing lanes it never touched before. Mars, then closer. Millions of years of patience narrow into a corridor, and the boulder slips onto a path that reaches all the way in toward the inner planets. Once through the door, the rock's fate was no longer slow. It was falling sunward, and something would eventually be waiting in its path. The long fall. So we have a rock, and we have a rough sense of the doorway it came through. What we don't have yet is a home. Not a region, not a family, but an address, the precise corner of the belt where this exact stone once belonged before anything set it loose. That is the question the whole story has been circling. Where was it born, and when? And the strange thing is, the answer isn't gone. It's still written in the way the object moves, in the tilt and stretch and drift of an orbit that has been keeping a record the entire time. Everything so far had been the setup. Now the real work began, winding the clock backward to the instant a distant collision set this rock free. Rewinding the orbit. The method sounds almost simple. You measure exactly how the object moves today, its speed, its angle, the shape of its loop around the sun, and you feed those numbers into a model of the whole solar system. Then you tell the model to run backward. The planets retrace their laps, gravity works in reverse, and the rock's path unwinds toward where it used to be. But nothing here is clean. Every measurement carries a tiny margin of error, and that small blur at the start grows with every step into the past. A hair of uncertainty today becomes a wide fog a million years back, until a single trajectory smears into a cloud of maybes. Still, the pattern is worth chasing. Reverse the sky far enough and orbits that look random today snap back together into a single point, if you can survive the uncertainty. 10,000 paths, so you don't trust a single answer. You take the rock's measured position, its speed, its brightness, and you nudge each number a little, once, then again, within the range your instruments allow. Every tiny nudge is a slightly different rock, a different starting point for the long journey backward. Then you run it, not once but 10,000 times, sometimes a million, each clone falling back through the centuries on its own thread. A computer plays every version of the story at once, and you watch not one orbit but a swarm of them, drifting and spreading like smoke in still air. The trick isn't any single path, it's where they gather. If the errors were random, the swarm would just dissolve into noise and tell you nothing. But if there's a real home hiding in the data, the threads start to lean the same way, crowding toward one corner of the map. At first, the path sprayed everywhere, a cloud of ghosts, but as the constraints tightened, that cloud began to shrink toward a single home. The cloud narrows. Watch the swarm long enough and something quiet happens. The stray threads, the ones flung out to the edges, start to fade from the count, and the dense heart of the cloud pulls inward. Run after run, the orbits keep pointing back to the same neighborhood, a specific band of the inner belt, where sunlight is stronger and the stones sit closer to us than most. It's not a pinpoint yet, more like a glowing smudge on the map, but the smudge holds still while everything around it dims, and within that region, the numbers keep brushing up against one particular family of asteroids, a cluster of stones that already share a color, a spin, a chemistry. The odds line up. The chemistry you read from the fireball, the orbit you traced from the sky, the family that's been quietly leaking fragments our way for ages, all of them agree. The ghosts had almost all landed in the same place, and that place had a history violent enough to explain everything. A point in time. And here's the strange gift of running orbits backward. You don't only get a where, you get a when. The same simulations that crowd toward one region also crowd toward one stretch of time, the era when this fragment first began drifting on the path that would eventually cross ours. It isn't a date you could mark on a calendar. It's a window, wide but real, measured in millions of years. The span it takes for sunlight and gravity to nudge a loose stone from its birthplace onto a road that leads to Earth. Count the drift, and the calendar pages fall away beneath you. Past the pyramids, past the first footprints, past the oceans you'd recognize, back into a silence with no witnesses at all. The clock stopped on a moment deep in prehistory, long before any human eye, when two ancient worlds met in the dark. The collision. Two bodies, each many kilometers across, closing at speeds you can barely picture, maybe 5 kilometers every second. When they met, there was no sound, only a flash of released energy, hotter than the surface of a star. Rock behaved like liquid. Craters wider than cities opened in a single heartbeat, and a spray of debris fanned out in every direction, glittering like a struck match in the dark. Most of that shattered material stayed close, still circling the wound it came from, a loose swarm of stone tracing the path of the world that made it. But some pieces carried too much speed to stay. They spun away from the family, tumbling end over end, cooling slowly as they went. Among them, one modest chunk, no larger than a boulder, caught the exact push it needed to begin drifting inward. In one silent, blinding instant, a splinter of a shattered world was thrown free, and that splinter would spend eternity falling toward a planet that did not yet have a name for it. Where it was born, the trail led to the inner edge of the asteroid belt, that crowded band between Mars and Jupiter, roughly 2.2 astronomical units from the Sun. There, orbiting in loose company, sits the Flora family, a scattered clan of stony fragments left over from an ancient breakup, exactly the kind of collision we'd just watched. Its members carry the right composition, the right brightness, the right chemistry to match the stone that fell. From that cradle, gravity and light did the rest. A resonance with Jupiter, a gap in the belt where orbits turn unstable, nudged our fragment toward the edge. Then sunlight took over, its faint warmth pressing on one side across millions of years until the orbit finally tipped inward. We can't point to a single crater and say this is the exact scar. The belt has reshuffled itself far too many times for that. But the region, the family, the mechanism, all of it fits. Now that we knew where it began, we could finally follow it forward, every million-year mile of the longest journey it would ever take. The journey home. So imagine you're riding it, you're a fist of rock and metal, turning slowly, one face catching the distant sun, the other frozen in shadow. Around you, the belt is not the crowded rubble field of the movies, but a vast emptiness, your nearest neighbor, often millions of kilometers away. You drift and you turn, and the sun is just a bright star you circle once every few years. Then, slowly, the circle begins to change. With every pass, sunlight leans on you a little harder, and your orbit stretches, reaching inward past Mars, crossing the lanes where the planets run. Whole civilizations could rise and fall in the time it takes you to shift a single degree. You are patient because you have no choice. For ages nothing happened, only the slow drift of an indifferent orbit, until one pass brought it close enough to feel a blue world's pull. The last orbit. That one pass changed everything. The blue world's gravity bent your path, pulling your long loop tighter, until your orbit no longer just wandered the inner solar system. It now crossed the line the Earth itself follows around the Sun, and once two paths cross, it's only a matter of time before they meet at the same point together. Your fate stopped being measured in eons and started being measured in years. Each trip around the sun brought you back to that crossing point, sometimes early, sometimes late, sometimes with the Earth nowhere near. For a while, the timing never lined up, and you slipped past an empty stretch of space where the planet had been months before. But the loops were narrowing, the near misses growing nearer, the gap between rock and world closing pass by pass. The solar system had been steering it toward this appointment for millions of years, and it would keep the appointment to the second. The final hours. Now the final loop tightens to a single day. You're closing on the Earth from the direction of the sun, hidden inside its glare, coming in on the daylit side where no telescope on the ground can pick you out against all that light. The one patch of sky no survey watches well is the exact patch you're falling through. Below, the eastern edge of North America is turning toward morning. Along a strip of coastline, Washington is still dark, the streetlights on, the first commuters barely stirring, hours from a dawn that will arrive with company. Nobody is looking up, because there's nothing yet to see. You're moving at tens of thousands of miles an hour, and the last of the distance is vanishing fast. It crossed the orbit of the moon unseen, unnamed and unwatched, with only hours left before the sky itself would stop it. The approach. Inside the moon's orbit, the Earth stops being a distant point and becomes a wall filling half the sky ahead. Its gravity has you now, and it's still pulling, adding speed to a fall that's already blistering. You're doing something close to 40,000 miles an hour, roughly 11 miles every second, faster than any bullet ever fired. For these last minutes, you're still whole, still the same dark stone that drifted for ages, cold all the way through, unchanged since the collision that set you loose. Nothing has touched you out here. No wind, no heat, no sound. Just the long silence of space closing behind you. That silence is about to end. Below the black, the planet wears a thin blue skin of air, a layer so faint that from orbit you can see stars straight through it. Ahead lay a wall of gas, thin enough to see through, yet at this speed it would hit like solid rock. Meeting the air. At first, the air is almost nothing. The rock is moving so fast, near 40,000 miles an hour, that even the thinnest gas can't move out of the way. Instead of parting, the molecules pile up in front of the stone, crush together faster than they can escape. That squeezing is the key. When you compress a gas that hard, that quickly, it doesn't just push back, it heats. The air in front of the rock climbs past 3,000 degrees Fahrenheit, hotter than molten iron, a cushion of glowing plasma riding just ahead of the surface. And here's the quiet twist. It isn't friction scraping the rock that lights the sky. It's the air itself, compressed to incandescence, wrapping the stone in a sheath of fire. The rock is barely warm inside, while its skin boils away, shedding glowing layers into the dark. The air did not slow it gently. It fought back, and the pressure building on the rock's face was about to win. The fireball. From the rock's own frame, there is no wind, no sound. Only a growing brightness swallowing the view ahead. The glowing air becomes a blinding wall, and every second peels another skin of stone away in streaks of white light. If you were riding it, you would see the whole sky turn to flame in front of you. On the ground, 60 miles below, it looks like something else entirely. A point of light appears, then swells until it outshines the full moon, then the sun. Shadows swing across driveways and fields. People later said the night went white, like a camera flash held too long, bright enough to read by at 3 in the morning. What they were watching was mass turning into light. Every flash was another piece of the rock vaporizing, poured out as raw glow across the state. The glow the whole state had watched was the rock burning away. But the true violence had not yet arrived. It was still being stored, in silence. The blast. The pressure on the front face kept climbing. Picture the difference. On the leading edge, air crushed to hundreds of times its normal density, and on the trailing edge, almost nothing at all. The rock is being squeezed from ahead and pulled from behind, harder every mile it falls. Stone is strong, but it isn't built for this. Cracks that had ridden inside it for 4 billion years finally find the pressure they need. In a fraction of a second, the whole body fails at once, not chipping away, but coming apart completely, exposing its entire mass to that crushing air in an instant. That is the moment the energy releases. Roughly 10 tons of rock, all its motion converted at once, dumped into the sky as heat and blast rather than a crater in the ground. It never touched the earth. It destroyed itself in the air, and the shockwave it left behind was the sound that had woken a state. Echoes. Go back to the instruments for a moment. The infrasound stations that caught a pressure wave far below hearing, the seismographs that felt the ground flex, the weather satellite that logged a flash from orbit, the all-sky cameras pointed at nothing in particular. Each one held only a fragment of the night. On their own, they meant almost nothing. But laid side by side, timed to the same fractions of a second, they told one story and only one. The altitude the fireball reached, the angle it fell at, the energy it released, the point where it came apart. Every number agreed. The rock that never landed had still left a full confession, written across half a dozen machines that were never built to work together. And that is the part that stays with you when you sit quietly with it. One rock's story was now complete, but it forced a harder question. How many others had ended the same way, with no one keeping the record? Chelyabinsk's shadow. To feel the scale of what nearly happened here, look east, to February 2013, over the Russian city of Chelyabinsk. A rock about 20 meters across came in low and bright, for a moment brighter than the sun. It broke apart roughly 30 kilometers up with the force of around 30 Hiroshima bombs. No crater, no impact, just a shockwave that reached the streets minutes later and blew out windows across 6 cities. More than 1,000 people were hurt, most of them cut by flying glass as they stood at those very windows, drawn to the light. That object was perhaps 3 times wider than the one over Washington, and the energy did not grow gently with size. A little more width, a little more speed, and the sky stops being a curiosity and starts breaking the things people are standing behind. Chelyabinsk was a warning felt by a city, but even it was small compared to what the sky had done within living memory of the land. Tunguska. Travel back further still, to the morning of June 30th, 1908, deep into Siberia, to the Tunguska River. Something entered the atmosphere and burst several kilometers above the ground, with an energy estimated at 10 to 15 megatons, hundreds of times the blast over Hiroshima. Again, there was no crater. But the forest below told the whole story. Around 2,000 square kilometers of trees were flattened, some 80 million of them laid flat in a vast radial pattern that pointed away from the center like spokes on a wheel. People at a trading post, dozens of kilometers off, were thrown from their chairs and felt the heat wash over their faces. It remains the largest impact event in recorded history, and it was caused by an object perhaps only 50 to 60 meters across. Tunguska struck an empty forest by pure luck, and luck is not a defense, which raised the question of how often the sky truly rolls the dice. The unseen rain. Every single day, Earth sweeps up something close to 100 tons of cosmic material. Almost all of it is dust and grit, sand-sized flecks that flare out silently in the upper atmosphere while you sleep. But hidden in that gentle rain are the larger stones, and they arrive far more often than you'd ever guess. An object a few meters wide slams into the atmosphere roughly every few weeks, somewhere on the planet. Most of them detonate over open ocean, over empty deserts, over ice sheets where no one is standing to look up. Military sensors built to watch for missiles catch the flashes, quiet little blooms of energy that no human eye ever sees. So the sky is not still. It's falling, constantly, in pieces too small to fear and just large enough to notice, scattered across a world that's mostly water and wilderness. The Washington blast was not rare at all. It was routine, and the only unusual thing about it was that this time we had watched. The census. For decades now, we've been building a map of the things that share our orbit. Telescopes with names like Catalina and Pan-STARRS sweep the night sky again and again, comparing images minute by minute, watching for the faint points of light that drift against the fixed stars. Each new dot is measured, tracked, and its path traced forward for a century or more. The effort began in earnest in the 1990s, and the progress has been genuinely reassuring. Of the true giants, the objects a kilometer or wider that could end civilization, astronomers believe they've now found well over 95%, and none of them are coming for us. That's a quiet triumph. A generation ago, we were blind to the largest dangers in our neighborhood, and now they're named, numbered, and watched. We have found nearly every mountain-sized threat, but the sky is not made only of mountains, and the smaller stones are almost all still missing. The ones we miss drop down in size, and the confidence falls away with it. For the objects around 140 meters across, big enough to flatten a city, we've catalogued only a fraction, maybe 40%. And below that, among the car and house-sized rocks like the one over Washington, the picture goes nearly dark. These smaller wanderers are faint, and they're fast. They spend almost all their time invisible, reflecting just enough sunlight to be spotted in the final hours or days before arrival, if they're spotted at all. Chelyabinsk gave no warning. Neither did the stone over Washington. So the uncomfortable truth settles in. The exact class of object most likely to reach us is the one we're worst at finding. Millions of these small wanderers cross our path uncounted, and closing that gap would require learning to watch the one place we never could. Watching the dark. The answer is finally taking shape in observatories and launch bays. A new space telescope called NEO Surveyor is being built to hunt in infrared, reading the faint heat that even a dark rock gives off long after sunset can no longer help us. Parked out toward the inner solar system, it can turn its gaze closer to the sun than any camera on the ground ever dared. Down here, the Vera Rubin Observatory has begun sweeping the whole visible sky every few nights, photographing the same stars again and again until the moving specks give themselves away. Between them, these instruments promise to catalogue hundreds of thousands of objects we've never seen, filling in the blind spots one faint dot at a time. None of it is finished, and none of it is perfect. But the direction has changed. For the first time, we are building eyes that can look toward the sun, and they may one day give the warning Washington never got. If it had been bigger, now hold the same event in your mind and simply make it larger. The rock over Washington was modest. A few meters of stone the air could tear apart cleanly. Widen it to 15 or 20 meters, roughly the size of the object that reached Chelyabinsk in 2013, and the arithmetic turns cruel. That morning over Russia, a stone about that size released the energy of nearly 500,000 tons of TNT, and the shockwave blew out windows across 6 cities. Around 1,500 people were hurt, most of them cut by flying glass, as they stood watching the strange light at their windows. A body only a few times bigger than the Washington fragment could do that to a city on any ordinary morning, with no more warning than a brightening in the sky. The difference between a spectacle and a catastrophe was only a matter of size, and the sky does not warn us which one is coming. The sky remembers. Trace it all the way back, and the whole story folds into a single arc. For something like 4 billion years, this fragment drifted in cold and silence, older than the oceans, older than anything that has ever looked up and wondered. It crossed our path unseen, hidden in the one direction our telescopes could not search, and it announced itself only in the last 2 seconds of a journey that had lasted almost the age of the Earth. That brief flash lit up more than the clouds. It showed us how crowded the space around our small world really is, and how much of it still slips past us in the dark. The fragment itself is gone now, scattered as dust and faint meteorites no one may ever gather. Its story had ended in a single flash over Washington, yet what it left behind in the record, and in us, would outlast the light by far. The new sentinels. The stone over Washington arrived from the one direction we struggle most to guard, the glare of the sun, where our telescopes are blinded by the very light they need to see. So the answer taking shape now is to stop watching only from the ground. Missions like NEO Surveyor are being built to drift out toward Venus and stare back at us with infrared eyes, catching the faint warmth of dark rock long before it reaches the daytime blind spot. Down here, new sweeping telescopes are learning to photograph the entire visible sky every few nights, comparing each frame against the last, flagging anything that moves. The slow work of the last few decades is turning into something steadier, a quiet shift from reacting to a flash after it happens toward simply watching, patiently, all the time. It's the beginning of a sky that finally notices what falls toward it. But for every stone we finally teach ourselves to see, another is already falling toward us right now, unseen and unnamed. The one still coming. The mathematics behind that is quiet and a little cold. Surveys suggest we've found most of the mountain-sized asteroids, the ones that could end a civilization, but the smaller stones, the ones that arrive as a city-sized blast rather than a global one, still number in the hundreds of thousands, and we've catalogued only a fraction of them. Each of those objects is following an orbit it has traced for millions of years, indifferent to whether anyone has written it down. Somewhere out in the dark, on a path we haven't measured, one of them is already on the arc that will one day cross ours. The next flash is not a possibility waiting to begin. It's a certainty already in motion, and there's no promise we'll be the ones to see it first. And this was never the first time the sky had done this. The Earth had been catching fire like this long before there were any eyes to watch. A rain across time. Drift back with me, past every telescope and every name, into deep time. For more than 4 billion years this same rain of stone has fallen, striking a young molten world, then empty oceans that flashed and healed, then continents of ice, then forests no one walked through. Every one of those arrivals was a moment like Washington's, a sudden light in a silent sky, witnessed by nothing at all. Trilobites saw some of them. Dinosaurs saw others. Most fell on a planet with no one to look up, one bright beat in a rhythm that was old before life learned to open its eyes. The blast above Washington was simply the latest, the first we happened to record so completely, a single note in music that will keep playing long after us. So the real question was never simply where this one stone came from, but what is left behind once the light above Washington finally fades. What the sky keeps. So trace it once more, slowly, the way you'd follow a river back to its spring. A collision somewhere in the belt, eons before anything here drew breath, cracked a parent body and set a shard drifting. Sunlight nudged it, orbit by orbit, until its path leaned inward and crossed our own. It came out of the glare of the sun, where no telescope could hold it, and for 9 seconds it burned above a city that felt the sky shake without knowing why. 10 tons of ancient rock, spending itself as light and sound over rattling windows and glowing doorbell cameras. Now it has a name, a birthplace, a story we can tell start to finish. And out in the fields, the fragments are cooling, black stones older than the ground they landed on, quiet again after 4.5 billion years of travel. The sky keeps no memory of them. It never has. We're the ones who remember. We caught this one note and held it, and that holding is the whole difference. So if you'd like to keep drifting, there are more of these stories waiting, more journeys home, written in fire and stone. Stay a while and let the sky keep talking.